Good. Can you hear me in the back? If you can't at some point during my speech, please, let me know so I can speak louder. Also, feel free to interrupt with questions. That's why I'm here, to be part of your discussion group, right? I'm here to talk about what a JVM does. But before I start my talk, I want to know how many of you are actually JVM experts. Then you're in the right place. And how many of you have spent time tuning JVMs the last week?
In the last week.
Okay. How many of you have spent time tuning garbage collection and JVMs the last year? Okay. Good. So I may ask you some questions later. No worries. All right. So who am I? To give a little bit of context, I see myself as a problem solver. I'm sure most of you are as well. I started off as a JRockit engineer back in Stockholm, where I'm from. That's my accent and my last name. What I was thinking on the plane here is why I've been in the JVM business for the last 10 years. And I think it's because of you guys, actually. You keep on innovating in Java, you keep on using it in good ways and weird ways, and it always puts a challenge on the JVM to kind of figure out how to make that perform better or faster or with less interruptions to what you're trying to do. And you also contribute to the Java language, which brings new challenges for the JVM to adapt to those challenges. So I ended up with the thought that I actually have you guys to thank for my job in the JVM business for the last 10 years. And I'm still intrigued, so thank you. I really like you guys. And yeah, I'm the product manager of Azul Systems, if you wonder what I do for a living. And I jumped there kind of after moving to the US and working for BEA Systems a while. That became Oracle, and I went through the whole Sun thing. But then I thought, I want to join a startup again. And when I heard how they had solved garbage collection, I kind of was sold on the idea. But I'm not here to talk about Zing. I've been warned to not even, this is not a product marketing opportunity, so I'm not going to talk about that. If you're interested, please follow up with me afterwards. I'm here to talk about what a JVM does. I especially want to focus on the compilers and the garbage collectors of the JVM, but I'm going to start up with some basics. And then I hope to reach, depending on how many questions I get, which I want to get continuously throughout the evening, I want to end up with, some last thoughts about what not to think about. And perhaps also mention what I think is the biggest challenge to Java scalability today. What do you think that is? I want to hear some suggestions. Yes?
Shared state.
Huh? Interesting. Any other suggestions? You have no problems when you code Java and scalability, it's all fine? Wow, you're the first group that never had issues with Java.
Yeah, we're Reading back here.
Ready?
Reading.
Okay.
How about the startup time? Big programs like Eclipse. Take a while to start up with all those.
That's annoying, yes. On my heart. I'm biased.
What was the comment?
Memory management.
What about system signaling?
System.
System signaling. Daemonizing Java processes.
Very good suggestion. I'm still biased. So,
Heap size.
yes, good. Heap size. Interesting.
Yeah. Which could be said more politely as long-running processes.
You're looking for a job? Anywho, to set everyone on the same level, the JVM is a software module that provides a unified execution environment to any job application out there, and that handles the resource management and execution. So you don't have to worry about the underlying layers. You don't have to adapt your program to each specific architecture. You can write your code, and the JVM takes care of the rest. It's the engine that executes your Java program. So a JVM does a lot for your Java programs, but as I said, I'm going to focus on compilers and garbage collectors. But I wanted to show you that it's more than that. So this slide lists a number of services that the JVM provides to your Java applications. I think time is too short to drill down for hours in each of these. That's why I cut them out of this presentation. If you're curious, I can give you follow-up material on these different topics. But for one, you don't have to worry about different thread models for different platforms. The JVM handles the dynamic code loading at runtime. You get access to all these pre-built libraries of functionality. All that is encapsulated in the JVM. But the key features that the JVM provides to the Java language is actually, in my personal opinion, the key features that made Java so popular. It's the portability. Maybe you've heard the expression write once, run anywhere. The JVM allows compile once, execute everywhere. It's the same thing. It's the JVM who enables that feature. And the other one, dynamic memory management. You don't have to worry where you allocate objects and where you free them up. Well, truth with modification, but still. The theory says you don't have to worry about that. So I'm going to start with portability. As I said, compile once, run everywhere. And this image is just to illustrate what I meant. You have your Java application, same code. You compile it into bytecode. That bytecode is the key to the JVM being able to read your Java code in any environment and execute to the underlying layers. No questions so far. You're good. All right?
Here's a question. On the previous slide, you said, the previous slide, that enforces type safety.
Yes.
What do you mean?
So, for instance, when you compile your code, if you're trying to change an object of a certain class into another class that it's not allowed to transform into, like a class casting scenario, then the compiler and JVM will not allow you to do that.
That's compiler, but there is a type erasure happens at the
Can you
JVM
speak
level.
up, please?
Type erasure. So if I have type collection, then all that information is lost at the bytecode level, right? So JVM doesn't enforce that type of a type safety. So if I declared my collection of, let's say, people, okay, at runtime through the reflection, I can add flower to it because it's all objects. So
He's referring to generics
well, I
erasure.
try to cast to curse, but in my language, I declare the type collection, but JVM doesn't enforce that type, right?
Yeah, well, the class cast is the JVM stopping at the last second. The compiler let it through. So actually it is the JVM. Isn't that class cast
That's erased.
at run? The erasure is the compiler, right? He threw it into the JVM and didn't tell him the type. But then your cast eventually didn't work. That would be the JVM, I would think.
The JVM didn't lose it, the Java C folks did.
Right. Anyway,
It's good, continue.
Out of scope.
yeah, I don't know.
I love this. It's perfect. It's a good question. I will follow up with you afterwards on that. I'm not sure if I got your question correctly. But we can stick for now that the JVM do look at class metadata to make sure that you are doing allowed operations. Fair enough answer for now. I don't want to drill down into it. So Java C, you're all familiar with, and that is actually a static compiler, right? It looks at your Java code and it creates the class files, or class file that contains the bytecode. But at runtime, that bytecode is kind of perhaps not optimal for the hardware that you're on. So what the compiler in the JVM does is actually look at that bytecode and either interpret it, which is a basic lookup for what those bytecode instructions are in the instruction language of the hardware architecture, or it can do a more intelligent translation to the underlying hardware architecture language. It can look at the bytecode and see if there is a better way of executing that on the very hardware architecture that you're currently executing on than just the simple instruction set correlating to that bytecode. That's clear? Good. So I like to use the image of either you have a dictionary, which is an interpreting form of bytecode execution, right, through the JVM's compiler, or you have actually an intelligent translator next to you that understands the context of what you're trying to do and looks at more things around it. It's called code profiling. That code profiling makes different choices of what specific instructions to send to the processor. Make sense? So how many of you know that there are different compilers in a JVM? Good. And now we're going to talk about something that someone over here, I think it was you, startup time. It actually has to do with class loading, of course, but startup time can also be if you interpret or if you compile the bytecode. It can be more or less advanced optimizations done to that bytecode, depending on what compiler you use. So there are different compilers for different needs, different compilers for different mode of running your Java application. One of them, and I'm talking about the lower part of this slide, one of them is the server-side compiler. The other one is the client-side compiler. The client-side makes less profiling of your bytecode, which leads to a faster compilation, a faster warm-up time before your program is fully interpreted or fully compiled. But the outcome may be less performant than if you use the server compiler, which looks at more data around your code, that performs more code profiling. The outcome is faster code to execute on that very platform, but it takes longer time to get there. Make sense?
Yeah.
This is what you sometimes see as startup time. Part of the startup time is not class loading, it's also bytecode compilation, just-in-time compilation. And if you're using a server-side compiler, it will do more effective optimizations onto your code, but it will take a longer time until you get there. So you can actually, yeah, do you have a question?
Yeah, could you comment on the efforts to bypass this altogether? There was an open source project that was with the various Linux distributions to just compile it all into static code, completely compile it, and why that was successful or why it wasn't successful. That didn't seem to go anywhere after Java 1.4.
I'm not sure I know what that very open source project is, but if you're saying that it was directly translated,
To the chip vendor's code.
Yeah, it's, actually, I think it's either GCC or another something
Yeah.
or the other. I'm not sure, but it actually translates directly to the native code to actually end up with different binaries basically for different platforms.
GCJ.
GCJ.
Yeah.
so that is that compiler for specific platform?
Well, yes, but it's for,
It was-
there's a lot, it runs on a lot of different platforms, but it produces native code instead of JVM code.
It uses the GCC backend,
Oh,
so
okay.
anything that you can produce code for from using GCC, it'll produce.
How does it handle libraries?
Well, and dynamic
Badly,
code
that's the
generation
problem.
is well.
So
It has to have an interpreter on board. If you generate code, it would have to interpret that
So
code.
here's my more general answer if you're comparing static compilation, one-time optimal directly to native code for the very platform you're on, or dynamic compilation that does the compilation concurrently with your program running or starting. Right? My general answer is that static compilation happens once, and then you run your application, and it may be great. But what if the load of that application is dynamic? What happens if the load changes and suddenly other methods are called more frequently? What happens then? A dynamic compiler that does it just in time during the runtime can actually look at what happens right now and recompile or decompile depending on what happens with your application during runtime. So it's more about context right there and then, and it can actually optimize over time, better and better, depending on what happens with the application. Does that make sense?
Is there some data on how often that actually happens?
It happens more often than you think.
That
No,
was my question.
no.
Is there some data on that?
So I have performance data, like how much more performant a code gets when using interpreted static compilers versus the client compiler versus the server compiler, but I'm not sure that is the data you're asking.
No, my question is, you mentioned one specific use case, which is what happens if the usage pattern during the runtime of my app changes?
Oh, you're asking how often
And,
that happens.
and I think that sounds like a really neat feature, in theory. It's just not so clear to me that this actually occurs in practice. And I'm wondering whether anybody has studied enterprise apps, long-running enterprise apps, to see whether they actually have mostly the same usage pattern or to what degree it changes.
That's a very good question, and I would like to see that performance or that statistic data as well. What I can tell you is my experience with a lot of customers that have web portal applications, and they have seasonal offerings like over Thanksgiving, Cyber Monday, or Black Friday. Suddenly, they 10 times the load on their app.
But
And
it's still the
those
same
are
usage
often
pattern. It's just more. But if Amazon during Christmas peak, it does all the same things. It just does more of it. It's not actually that the code flow dynamics change. It's just more. So that's exactly the point.
But if you have a sales campaign that has suddenly new features available, that you can compare sales prices instead of the regular prices, that may actually.
Yeah, okay. Now we get into
Positive.
speculation again
Yes.
as to how often
Yes.
this happens. My
I
question
would
was,
like
how
to
often does it really happen?
Yes,
Okay,
correct.
we don't know.
It's speculation.
Okay,
I can just share my experience.
okay.
Can I comment on this?
Yes, sure.
So if your enterprise app has any sort of batch processes which interact with your running services, that would pretty much guarantee that your usage patterns would change. I don't know. Batch processes are maybe scary to some people, but they exist pretty much everywhere.
Well, heavily contended resources need different access patterns.
We can't hear you if you mumble in the third row.
Give us a bad name.
That heavily contended resources need different access patterns than lightly contended resources. And so just using it 10 times as much does affect how you use it. If you throw a couple orders of magnitude at how you access a lock now, all of a sudden, spin locks look a lot different than different kinds of locks.
So the other thing, having worked a lot with the runtime profiling, is that actually getting good profiles to use to statically optimize is really hard. And I worked on a number of teams that discovered that the profiles we were running to optimize the code were producing worse code in production than if we'd done none at all, because they were the wrong profiles for what our customers were using. So while you can get good profiling if you do runtime profiling, it's really hard. And a lot of companies are starting to move toward the dynamic model because you get it right the first time. You just deploy and it works. And trying to actually figure out how do I get the test cases so that I get the right data that makes it work well is really hard. You think it would be easy, but repros are surprisingly difficult and often wrong when they sit in test on for a year.
That's a very good answer. Thank you.
I think that the dynamic one actually gets it wrong the first time, but then it fixes itself.
That's right.
Is there any JVM instrumentation to see actually when this happens, to look at the...
So when the optimization threads
and
kick in?
it kicks in, you can see it changing as it, monitoring the JVM.
That's a
There
good
are command
question.
line switches to
What?
get traces when that stuff's going on. There are command line switches to give you traces when various optimization happen, at least in the Sun JVM. But it'll vary for every JVM though.
There are also profiling tools that you can run on the side, but I don't know all of them. Yes?
I'm just a Java developer who throws the code at the JVM, and I had always assumed that these JIT compilations, we started with this term JIT, and I thought it just did its compilation, and maybe it can do it even better with a C2, but changing usage patterns, oh, here's some code I haven't JITted yet. Why is that not the right model for me as a developer sitting on top of the stack? The usage patterns change, it's just really going to go back and say, well, we're going to do it different over here. Is there really features in the JVM that do that?
Yes. There are
Well, okay, hotspot, that's a third level of optimization, a local spot that's had a lot of activity. But you can, it's drilling in and in and in. It doesn't drill back out and rearrange it, does it?
Yeah, it will
It could.
unoptimize.
It could. Okay. No, I actually it does. I'm just.
No. It could depend on what your application does. I mean, in JRockit, when I was in that team, we had optimization threads kicking in once in a while to check if there were new methods being.
See, that's stuff we haven't optimized yet.
Okay.
That's just more and more, and eventually it gets all jitted and it's sort of done.
And in Zing, our JVM, which I was not supposed to talk about.
That's okay.
We actually do decompilation sometimes, because if you do a compilation on a certain set of bytecode, and then you analyze that after more profiling being done, that if I do this optimization instead, the outcome will probably be more performant than just optimizing
Okay,
this
so
little
try
piece
to
of
get it a
code.
different way.
Yeah, so you can do certain things, but then as you collect more data over time, things look differently, and you do recompilation or decompilation and recompilation again.
Okay.
It depends.
It all sounds good, but also a little bit abstract. Can you give very specific examples?
Thank you. But before I do, it's the next slide. Before I do, I want to do one really, really important thing that goes for all JVMs. Think about this. To do the optimizations, we as in the JVM, we need a little bit of resources. Don't forget that when you calculate how much memory your Java app actually will need. So some JVMs put it into the XMX flag, like it's in the heap size, and they take away a percentage of that for the JVM. Other JVMs have it outside and take your XMX value and adds onto it. So when you look at how much memory your Java process actually has, it's bigger than the heap size suddenly. It's this. It actually requires some space. So, and for some JVMs, you can actually modify that if you want more aggressive. If your application is written in a way that requires more aggressive optimizations, which need more space to keep the profiling data, run your bytecode, you may require more. And if you want more threads or require more threads to do optimizations over time, especially in the enterprise server side, you may need more of that space. And we have so many issues, we as in the JVM land, because I've worked with several different JVMs. It's all a common issue that people don't remember that the JVM itself also needs some resources. I'm moving more.
So what is more aggressive? Like how often do these recompilations occur?
So that's the same question that over here. It's tied in. It's a very good question. So how often does your application change behavior, or which compiler do you use? The client compiler definitely does less compilation than the server one. And then you can have different algorithms, depending on what JVM you use, how that DE optimization, VE optimization, or new optimization kicks in. So how often, I think you will need the profiling tool that these two gentlemen talked about, or the command line option to spit that out to see what is the truth for your application, because it's different. Yes?
Does the JVM keep track of each attempt it made and pick the best one, or does it ever get into an oscillation model?
Depending on which JVM you talk about. I would assume that all JVM actually keeps track of what it's done and not do it over and over again.
But even the past failures?
Yeah.
So it doesn't try those again?
I think there is a time limit sometimes, because if something was correct and then discovered to be incorrect, and then later it is correct, you don't want to miss that chance. There are also bugs that kind of makes that happen to some JVMs, no names.
Not Zing,
No.
Somebody else's.
Not Zing.
If you've had a JVM that's been running for a while in production, and you wanted to store that profile, and then start with that profile again, because you don't want to have it, maybe it takes a couple weeks to optimize.
Excellent question. Sorry.
Yeah, so that, is there such a thing? I've never seen.
So I don't know if you heard the question, but if you run an application and you do all these optimizations, is there any way to kind of store those optimizations made somewhere, so you can apply it again once you restart the application, so that time doesn't have to be occupied for optimizing it all over again? I've been involved in projects where we tried to save out what was in the code cache, which is where optimization instructions are stored. Sorry, I'm going to back up a bit. Bytecode, when it's compiled, optimized, the corresponding instruction set for a piece of bytecode instructions are stored in the code cache. And if it's optimized, it's replaced with those new instruction orders, instruction sets. So the code cache is the storage for what you should execute when you hit a certain piece of bytecode, right? What's in the code cache is the optimization. So what if you could flush that code cache out to file and then load it the next time the JVM starts? Would be a great idea. I've been involved in projects where that was successful for in-lab applications that are exactly the same every time you run them. But then the randomness of user load in real production environment screws that up. Because what guarantees that the same, if 10 users log in at the same time to an application, that happens at the same time as someone else is doing some big calculation of a transaction they're going to purchase some Apple stock or whatever. What guarantees that happens at the same time, the next time? And what guarantees that it doesn't behave differently?
So you have to recognize the
Right.
profiles as well.
Right. But it was just like a starting point. So at least it's not something of course things are going to change, but
Yeah.
at least it gives you a starting point. If it take, I don't know, how long does it take?
I think it's an excellent idea. We tried it, it didn't work in production.
Okay.
But here's an idea. Why don't you try it? And then you call us and we hire you. It's good.
Sounds fun.
Yeah.
Ask a question. What granularity of the optimization you're talking about?
Sorry?
What granularity of this optimization? You said, so JVM runs, you learn some profiling, what allow you to optimize. Do you apply it next time, say JVM next time start again? Or you can apply it when you load next classes, specifically to that classes, different time, or to everything. So was I clear? So how it is, to what this new optimization rule can be applied and when?
I'm not sure I'm following. Was it related to the previous question? Because we don't do that. We don't reload optimizations that have been made. But I'm not sure I
I
understood.
think the question is how often do the optimizations occur? Is that right?
Optimization means so once I run some code in JVM and I learn it should be compiled differently. It would be better if I compile it differently. When I applied those rules, when I start my JVM next time, when I load next class to same JVM during running.
Okay, so it's differently implemented in different JVMs. So the question is, when does the JVM decide to do a recompilation or re-optimization? When does it decide to optimize? There are different algorithms and different implementations in different JVMs. One is to look the decision of what to optimize. I can start with answering that one. There's a very simple approach, but it's just one of many. It can look at what method is called most often and decide if that method is able to be optimized, if there's some optimization to be applied to that method that makes it run faster, it actually makes sense to pick the most run methods to optimize, because those are the ones impacting your running application performance the most. Does that make sense?
Okay, yes. So it's for next start of JVM.
No.
Same run, the same run.
So it's always.
Totally dynamic.
So either it's startup time when you look at the bytecode and you compile it the first time for that hardware architecture where you're on, but then there are threads running concurrently with your program, looking at different things and doing the code profiling while running. And if it turns out that a method is called 10,000 times a second, it makes sense to look if that method should be optimized. But that analysis is doing concurrently with your application running. And the heuristics around when that kicks in is different in different JVMs. You can either do it like with regular time windows, every other 30 seconds or every other second. It's different heuristics how you do that in different JVMs. So you both do it at startup and while running, while calling a method or while loading a class, you look at that code and you optimize it or you compile it. Or when your program is up and running, you do code profiling and looking at you
So
know,
for changing specific code which already run, but it's not applicable to new classes which will be loaded first time.
the first time a class is loaded, you look at the bytecode, you look at what instruction set corresponds to that bytecode for that hardware architecture you're on. If there is an optimization in the code cache already for a similar bytecode instruction set, it can be similar to some other class instruction set. You use that one, but otherwise you generate instructions.
Similar in sense of sequence of instructions. What does mean similar?
Yeah, I think. Does that address your question?
Yes. Of course, it may be not optimal, not necessarily similar sequence can be optimal in other context.
Sure, but then you have later on the feature of looking at that in a bigger context and understanding it better over time with more profiling done to that code piece, and then you can choose to recompile. But it's better, it's like 5 times better to be compiled than just interpreted, performance-wise. And it's, you know, I'm talking about the server compiler. It's 4 times better with the client compiler, and it's actually 6 times better with the tiered, which uses profiling data from the client compiler but applies optimizations from the server compiler.
So, I'm sorry, can we want to move on? Because we've been stuck on this slide for like 5 minutes. I just want to stay here
I'm sorry.
till the end.
We're gonna run
It's
out
been
of
more
time.
like 10, but
Okay.
if we're counting, yeah.
To your question. Some examples, and I'm not going to talk about Zing, but being a product manager, I had to put my product in any slide. So, at least this one. Here's a little code example. A method called time to scale my app, and if you had endless of resources, you know, you could probably re-architect and use Zing, which would be great. If you don't have endless of resources, you can use Zing and it'd be great, right? But if you look closely, you know, this little variable here, hatched by clustering, you know, is never used in this specific bytecode context. This is not bytecode, but you can imagine the bytecode instructions corresponding to this method. Yeah, what can you do? Well, you can do something called dead code elimination. It basically just doesn't perform that instruction of assigning that value to that int. It just doesn't do it because it's actually not used anywhere. So that's one very, very common example of an optimization in the compiler. And of course, this reduces the bytecode size and it prevents, you know, unnecessary operations in the processor that can be used for other stuff.
Can you clarify which compiler you're talking about here? Because I mean, you've mentioned there's the
question.
Java C compiler, there's the compiler in the JVM.
Right.
I would assume this is done at the level of the Java C compiler. No, this is actually only done at the JVM. It doesn't realize the Java C, even though that's clearly a local variable, so there's no possible usage, can't be exposed. It's actually only done at the JVM.
So Java C
Yep.
is checking, you know, different things that you are allowed according to the Java spec. So it warns you if you don't do the code correctly according to the spec. It should warn you at least. And it also translates exactly your methods into bytecode.
So no optimizations occur essentially at
Not
the
that
Java
I'm aware of.
C. Interesting.
People looked at doing
Maybe
that.
maybe
It screwed
someone
up
can prove me wrong, but I'm not aware
Yeah,
of it.
originally there was an optimization flag, but it never did anything in practice. And now
Well, and the hotspot guys found out that when your pre-compiler starts removing stuff, you lose intent, and so they would have liked to have that information to do more sophisticated things with.
So Zing actually
It stepped on their own
removes,
toes.
like primitive assignment instruction, or what if I got a method called and assigned to a variable? Does it remove it as well?
So any JVM does this.
Just
it's
the-
not Zing specific. I want to answer
Just
you.
a primitive assignment like an int
Mhm.
variable right there. So it remove primitive assignment variable that's not used.
Yes.
But if it's, say, I've got a method call that actually executes something, that returns something.
And this something is never used, and the return value is never used. Is that's your question?
Right.
So you're thinking that if it's a...
So what am I calling something that I actually wanted to call? Like,
Mhm.
you know,
But then
forcing
you
it
know
to
it's-
load something in the method and
But-
assign it to something. Does it remove that? Well, I guess it's a two instruction. I don't know.
So I'm not sure I understand you
I think he
correctly,
means
but
if there's a.
I can
if
repeat
you-
what this is, which is you are sure that
Right.
this is not being used anywhere.
Right.
Because it's within the method and it's not a global something because it was declared here. It's a very local variable.
Like instead of 15, like a method call that returns.
But then you have to look at that method as well to see what that comes out. And maybe if this is a method call that does something else, you may not end up removing it. But still,
So assuming it has no side effects.
assuming it has no side effects, it will remove it. And it may actually even remove that call to the function if it's a smart enough compiler. But I can't stand here and think of all the special
Scenarios.
cases that might come and bite me later if I say, yes, it will remove all.
Okay.
Because I'm not an expert in compilers, believe it or not. I'm a garbage collection girl, and I haven't come to that point.
Just one thing to clarify my question. I mean, I'm familiar with a lot of the optimizations, I think, but my question was really like, an optimization like this, you would never come back to it. So I would be very interested in examples of where a new code profile would actually change optimizations that you've done earlier. That's just maybe for
Well, like a
later bit.
If we loaded a class,
That's not appropriate.
virtual method, and then optimizer inlined it, and then you loaded another class which overrode that method, that inlined method would have to be de-optimized so that it could.
Yeah, that's
And area in
correct.
the
That's
back row,
correctness.
and
That's a
then-
correctness problem, not a performance problem. Though, so.
Yes, it can be de-optimized for various reasons.
I'm going to remove Okay. So let's see. I could skip my other examples and just move into garbage collection. I don't know if you want to.
Yeah.
What do you want to
Do
do
it.
now? I just had some really great ones here. Inlining is when you.
You can go through it pretty fast. We'll go slowly on the video playback.
Okay. Well, you will have access to these slides later, right?
Oh, okay. Sure.
So
You guys wanna
you
go?
can, if you're really interested in all my little fun examples, you can do that. So to sum up compilers, so we can get into the garbage collection stuff. What the compiler does is basically removing the pain for you guys to have to learn every hardware architecture instruction set. And if you use a static compiler, you may have a great performance for that little tiny app that you have a very restricted environment for, but the JVM's dynamic compiler can actually adapt and do things with more information around the context you're in. And maybe that takes some of your resources for you, and maybe it kicks in and takes some CPU load for you to do certain executions, but it is worth it in the end. If you compare an interpreter with a dynamic compiler, the performance outcome is 5x, as I said. Depending on what you measure, but the average is 5x. I have 10 minutes left. I think we have to come back and talk about garbage.
We have an hour, so.
Eva, why don't you just move along to garbage collection?
Yeah, you guide me.
But you have 10 minutes of the presentation left, you said? Or?
Yeah, I got the signal.
We'll leave room for questions if anybody.
Okay.
Well, we're going well with questions.
We have an hour in terms of like time, so it's
So the other thing is memory management, dynamic memory management. You don't have to, like in languages like C, you have to know exactly how big it should be and exactly where to allocate it and exactly where to free it, and you have to remember to free that up, you know. The garbage collector and the dynamic allocation of the JVM takes care of that. So all you need to do is, you know, create a new Zing fan down there, Eva, and you don't have to worry about the rest. It's going to be there when you need it. I'm trying to speed up. So there are basically many approaches to garbage collection, and maybe you already know of a few. You've heard of parallel garbage collector maybe, and you've heard of concurrent garbage collector. Do you know what that means? Because otherwise I'm going to tell you.
Less pauses.
Wow, you're my star. It creates less pauses. One of them do, yeah. But we're going to talk a lot about pauses here. So before I start, I want to again give you an understanding what the Java heap is. Just figuratively speaking. The Java heap is where all of the Java objects are allocated. And then we have that, you know, again, reminder, there's some extra space needed there for the code cache, for VM threads doing the profiling, and for the garbage collector structures that are needed to do garbage collection. So just keep this, if you learn one thing tonight, this is it. And if you want to know your exact total memory footprint, you can use that command there. That's the next one. And you specify the Java heap with the excellence. You know that, right? So, on the allocation phase, before you do garbage collection, you have to actually fill up the heap. And what some JVMs do, I'm not sure all of them do, that's why I express it some, is to actually to enable thread concurrency so that the allocation is not single-threaded. You actually allocate part of the heap to one specific thread, so it can keep on allocating the objects the Java program needs, but not conflict with other threads. If you didn't have this and just allocated on the heap, a lock would have to be taken every time a thread allocates something, otherwise they could conflict on the address space, right? So this is a very smart innovation in most JVMs to actually dedicate a certain part of the heap for a certain application thread. And it's important because this will lead to a problem. Okay? Here. First of all, when an object can't be allocated of any of the Java application threads anymore, the garbage collection is kicked in. That's, you know, pretty straightforward. But what you also notice here, which I will go into later, is that, you know, you don't have an exact fill-up of all these thread local areas, right? It's called fragments. And I'm going to talk about parallel garbage collection first. At the time of garbage collection, which is when you can't allocate anymore, actually all threads are turned into GC threads, garbage collection threads, and follows all the references and finds all the objects that are still referenced, which are called live objects. The ones who are not found through references are dead. They're not used anymore.
I'm sorry, but is it still a mark and sweep then?
Yes. There are, that's a very good question. Maybe I need to bring that up. The question was, is this still a mark and sweep approach? And there are a higher level of different garbage collection approaches. I've chosen to only talk about the market sweep collectors because those are the ones I'm most familiar with and the only commercial ones that I know of. There are other approaches called copying garbage collectors, which basically uses half the heap for allocation and then continues to allocate the other part while collecting the full part. So they kind of copy the live objects from one part into the other part and continues allocating that. And then they swap each part. It's a very resource wasting approach. You can only use half the heap all the time. But there have been successful deployments with that in the past. It's just not an approach that are commercial anymore with a market-leading JVM. I used the word market, sorry. Yes?
We have different garbage collectors for different spaces. But I thought like for the young generation, whatever you call it, there was like you use e-copying.
Yes, that's correct. I put a higher level truth, and I will go back to that when I talk about nursery. But you're right. But let me drill down into that later. You're very right on that. When you talk about the old space, I'm going to continue talking about that. But for the big heap, if you don't have a generational collector, copying is a wasting approach, in my opinion. Okay, so when you marked all your objects, the ones who are not found are collected. And again, the parallel garbage collector turns all the application threads into GC threads, mark everything, and then collect the dead waste. And then they turn back into application threads, and you can continue allocating whatever was blocked before. This means all application threads are blocked for a certain time. That certain time is the time it takes to follow all references through the entire heap, collect the dead one, and then bring it back up. If you don't care about pause times and just throughput, like for the most benchmarks out there only care about throughput, never response time. This is an excellent garbage collector. Yes?
What's the advantage of having 20 threads context switching all the time, garbage collecting instead of just one not context switching?
Depends on what you're trying to achieve, what the advantage is. So if you have 20 threads collecting garbage, it actually takes faster time, but your application is stopped. If you have one, it has to do all the work itself, right? But if you're on a small system, maybe, 20 threads doesn't matter, right? You still can do fine. So it depends on what environment you're in and what you're trying to achieve. Does that answer your question?
Also doesn't the system
Thread
actually
local.
change? I mean, your one thread is trying to follow references, new references are being created, or new objects are being allocated. Isn't the system sort of changing dynamically on you also?
The world stopped.
No, stop.
Well, I may have interpreted the question differently because it was a general question for garbage collector. Maybe you meant the parallel one. In the parallel case, if you have one thread, it will take longer time for that thread to do all the work than if you had 20. If you do have 20 cores, right?
Oh, okay, if you have multiple cores.
Yeah.
Yeah.
If you only have one core executing work, it doesn't matter if you have 20 threads.
Well, I would think it would, because if you only have one core, then you got a context switch between 20 threads.
Yeah, it would be worse.
That's
what you're saying, if you have more cores.
Only if you have more cores.
Yeah. Okay. So within the parallel garbage collector, that is the answer. I was jumping ahead to the next slide, so sorry for that.
I just have a quick question. When you said that the application threads turn into garbage collection threads, you mean just that it's the same thread, but they're now executing garbage collection code and different instructions, and then return back to what they're doing previously?
It could be that, or it could be that you have a pool of garbage collection threads that start when your application threads are stopped. So, but you can still utilize the cores underneath, and usually,
Oh,
yeah. So
so
you can
say
actually
turn into, you don't necessarily, it doesn't, it could be different threads or
It depends on what JVM you're talking about. But turn into, let's just say that you have a pool of garbage collection threads that are doing nothing until garbage collection kicks in, and then they do the garbage collection work. Make sense? Okay, moving ahead, trying to be quick. We're good?
You got 50 minutes, so.
15?
50.
50.
Yes.
So then we move on to concurrent garbage collection, which is actually executing concurrently with your Java application. Your Java application is continuing to allocate, while some set of threads are actually following references and marking them as live. And all the new objects that are allocated by application threads are marked live. That may be a bit of a waste at the point where dead objects are reclaimed, the space that they occupy, because this object foo here could have died before the garbage collection marking phase has ended. But that's a minor waste for the advantage, which is you don't have to stop all your threads for a long time. There is 2 or 3 or more, depending on what JVM you use, that actually has to do a mini stop just to sync up the rest of the world. But that's usually so small you don't see it. So concurrent garbage collection is concurrently with the Java application threads, and it doesn't stop all your threads to do garbage collection, but I'm going to continue what they do when they stop. So, sorry. I talked about the fragments. They can either happen during filling up of those thread local areas, and it's not an exact match of the objects you allocate to the space that thread local area, the size of that thread local area. There's also another way of fragments being created in the heap. It's actually when dead objects have been, the space where dead objects have been reclaimed, but then a new object is too big to fit in these spaces that are available on the heap. That will also trigger garbage collection. But more importantly, what if these objects are live? You still can't free up enough consecutive memory to fit that new, bigger object. So what to do here? There are 2 approaches. One is nursery. Now I'm coming back to that. It's actually the theory that most objects die very quickly. And if you separate the space of the heap to be the young space or the nursery or whatever you're familiar of calling it, it's a space where you allocate all the new objects and you perform a copying collection, meaning that when you can't fit a new object into that young space, you move all the live objects up to the old space and reclaim the dead objects in that space. And if you do this, several times, you see that, by copying up only the surviving objects of the young collection, you actually reduce fragments of the heap. And this line is just symbolic. You have large young space or small young space, large old space, right? It's usually a command line set. And that is one way of reducing those fragments. I'm building up to what the scalability issue is for Java here, if you're wondering what I'm doing. So another way to eliminate fragmentation is to actually move objects together. Right? It's a very expensive operation to move an object because you have to go through and update all its references. And that could be, worst case, the entire heap. That could be a very, very long pause because even in the concurrent garbage collector, when you move objects, which is called compaction, it can be a very long stop. Unless you use a specific JVM that has solved garbage collection.
Can you just sort of explain what you mean by long? Everything's relative. How long is long?
Very good question. Everything is relative. So my answer, everything is relative. If you have a large heap with a lot of live data, with a lot of references between the objects, complex data, right? That will take usually a few, tens of seconds, and large meaning gigabytes of heap size. And I think there's a per 2 gigabyte heap size, there's another 10 seconds of pause time with most JVMs. Then there's certain JVMs who have implemented concurrent compaction, where that doesn't matter, but it's very unique. Yes?
How do you decide the ratio between the young and the old generation size?
By tuning, endless tuning, unless you use another JVM. Keep on coming back to that. Yes?
If the cost is more to do with the references being updated than it is to the actual moving of the block of memory, then do any of the JVMs use a level of indirection? If you pointed to a single object that itself then referenced to the main block, you could move the block, change one reference, and all the other ones wouldn't need to be changed, right? If you put another, so now all your object references are actually double references. You're pointing to kind of a thing that marks where the object is, but it's the only one that really knows where it is in memory.
I'm not sure I'm following you.
If the problem is to change the references, another way to solve that, is to have is instead of having direct reference to the object for all the references, you refer to another intermediate, right, that then actually points to the block of memory. Now you can move the block of memory, and you have to change one object, right?
Do you want to get higher?
Actually, Sun already tried that in JDK 1.0.
Oh, really?
Object handles.
Did they stop doing it?
They stopped doing it because now every memory reference is double indirection.
That's right. That's the
And
trend.
in a mostly object.
Hang on.
Right.
If you do it on the actual, virtual memory address level, and use read barriers to check if you should update references or not, it's going to work.
So I think
But
that falls
it's a good idea.
Okay.
I think that falls into the classic space versus time trade-off. If you
Wow.
actually did it.
We're going to be philosophical here. No, I'm just kidding. Sorry. Yes, it's true.
I didn't quite catch which one of those objects. In that particular drawing there is that object no fit. Did it just come into existence in the old generation? Or was it's sitting in...
So it started off in the young generation.
Well, it's not there yet. I don't see it.
I think it's an error in my slide, perhaps.
And
No. Okay, it was the next slide. So object no fit is a young generation object that can't fit into old space
cannot
anymore.
fit in the old... I see. You're trying
What
to
do
move
you
it
do
up.
then? Because young space is a good solution to postpone more
Compact.
fragmentation, right?
And now you still have fragmentation eventually, and now what do you do?
Yes, sorry, that's a very
You,
important key point that I
you move them together. Where you moved them by you did compaction. What was your definition of moving them together?
Yes.
Push them together.
So you actually take an object and you change its address to be next to the space where you want
So
to
you had to take the hit to move object foo, object bar, and then you could move up object fit.
Yes,
Or
and that
object
hit
no
is
fit or whatever.
costly, because when you move object foo, you have to update all the references that are, you know, referencing to object foo.
And that's all kept track of in the VM, who references who?
Yes, by traversing the heap in most JVM. It's an expensive operation, and it will hit your, even the concurrent garbage collector will hit this case. And your pause time, I don't know if I fully answered what worst case is, but we have seen in enterprise Java server side where you have 2,000 concurrent users or something like that, and you have a heap of, let's say, 16 or 20 gigs. They have minutes of pause times because of this. That's funny.
So
They
when
shouldn't
you
have
have
to
to
have
compact the older generation, it takes minutes. Is that what you just said? On a giant server?
Only the compaction takes minutes.
Only the compaction takes minutes.
But that's only, I mean,
So every 30 minutes, your whole app stops for 30 seconds.
That's on a 16 or 20 gig memory box, though, right? I mean, was that the point that it's...
see, I mean, it depends on the app. If you have a lot of memory live and you end up in these fragmented heaps quickly because of, you know, either you don't have a young space, you don't postpone it, or if it runs long enough, you will hit a very bad state of the heap. And you will have to shut down everything to move every object to find that space to allocate the new object. That is a long time. If you have, especially if you grow beyond 4 gigs. Now back to what limits Java scalability today. If you have response time SLAs of, you know, 100 milliseconds, I don't know,
Less than 30
you will
seconds.
never be able to scale beyond 4 gigs. And what happens then when the machines grow in memory, like look at the new Nehalans, it's cheap to buy a 100 gig box today, but you have to have all these historical small instances of JVMs to actually utilize that resource.
So why specifically 4 gig? What happens? Is that because it's a 32-bit boundary, or is there something?
It's
Well,
a sound barrier.
It's just, yes, the pressure wave builds. Yeah.
So to summarize it, generational GC with the young space, it helps, but it postpones, doesn't solve it. Compaction will happen, it's inevitable to run long enough. For some applications that's just a few hours, but still. That's why benchmarks never show this, by the way. There have been many approaches to improve the compaction time, of course. That's a lot of hot innovation area in the JVM land. But they still mess up and do a long pause in the end. For instance, partition compaction, you choose certain segments of the heap and compact only those. But if you run long enough, that won't help in the end. And you may end up in a very bad area that has a lot of references and you end up stopping the world. So someone came up with, you know, why don't look at certain areas and pick them more dynamically? And, you know, there's just tons of interesting stuff. I'm going to try to keep moving on now because we're running out of time. But you can do reference counting into those areas to decide what areas to compact. But, you know, in the end, you will have to move an expensive object. And this can be tuned as well. Talk about tuning. It's a real world customer spend hours. And
Does
this
Windows
is common.
allow command
This is a
line?
common JVM optimization startup command line in many enterprise Java. deployments. I see this all the time with other JVMs, right? And the minute a new feature comes in that becomes really popular, you have to redo this over and over and over again. That's why I asked how many had spent time with JVM tuning. This is what you do. This is where you end up. I feel sorry for you.
Is anyone doing preemptive compaction when it's not needed per se on idle time?
When is idle time? What if the active application threads changes that object? How can you keep track of that area?
I mean,
while we're in the
I'm just saying for web applications, lots of times there's no web request coming in at that
So
particular
like
moment.
system GC, you do system compacts or something like that? Interesting. Want a job?
Not in California.
You can work that out.
So you have threads analyzing your code at runtime to optimize it. Are there any threads that are looking at maybe the sizing of these thread local spaces dynamically, or maybe the line between young generation, old generation spaces and sizing those dynamically based on?
Very good question, and that's called garbage collection heuristics. There are a lot of research projects, and you know, I don't like to bring it up, but my patents are all in garbage collection heuristics. The young space, old space sizing dynamically, I have seen it in one JVM that I worked with. There's a heuristic on deciding how long you should spend time on compacting a certain area before giving up and just leaving it be. So you kind of say a best chance of hitting a certain time of compaction. There are dynamic modifications during runtime of those limits as well, but usually it doesn't improve the worst case. It could be tuned like this for one specific application during one specific scenario, and it runs great. But if you dynamically change it, it may actually be impacting performance, and some people don't like that. In other JVMs where it is dynamic, it may actually be worth the cost of maybe have a lagging level. But what makes that true for the next round of garbage collection to actually do the same approach then? It's hard to decide, because then maybe another object that has a lot of references has been placed elsewhere in the heap, and it's very complex. Maybe I derailed.
Well, I mean, it seems like recompiling code is more complex than maybe, you know, picking these settings as you're running, right?
I don't know how to answer that because I'm so biased for garbage collection, and there's a war, believe me, between compiler teams and garbage collection teams of what is more complex. So I feel guilty, but I'm trying to be objective here. I think both are very complex, but bytecode will correspond to a certain set of instructions in the end. While you don't know when an object will be allocated and how many references it will have ahead of time. If you do something for a certain method, it will be saved, and the same thing will apply next time you call it, and it will still be performant. When you do a garbage collection, the heap will look totally different every time. That's my answer, the best answer I can give. Yes?
Regarding all those tuning parameters, I really like JRockit, where you have a parameter where you could say basically tune for throughput or tune for cost time.
Thank you.
That saves me a lot of
Yes, but that's again the best approach. It's not an exact formula, and worst case will happen in those times too. I'm sorry for that, but that's history. That's 10 years ago.
So my question has to do with the tuning as well. I mean, I've played around with some of those before, and it seems to me that sometimes you could go too far and straitjacket the JVM itself by taking away from it what it would really like to use in certain cases, or adding where it doesn't need it. And, I mean, would you suggest that people sort of like, hey, unless you really know what the heck you're doing, don't ever touch those things, and use more generalized approaches like what was suggested here, where either just do switch server or client, or at the very minimum deal with allocating size. But boy, I can get in a lot of trouble with trying to tune too much of this stuff, and then suddenly your system can't do anything because you're giving it opposite instructions and you don't know it.
I apologize. I have a new favorite. No, it's hard to say. I mean, if you have a simple application, which I doubt any of you actually has a simple application, but if you do, then spending time tuning it may be fine. But the minute that something changes, you will end up there again. That's my.
I mean, imagine if I came away with something like that, I'd say that's ridiculous. I better stop. That's crazy.
I agree with you, but it's about what they have to deal with. They have a 4 gig heap. How can they meet their management requirements on SLAs and customer demands and utilizing resources to that without doing this? If you're stuck with that kind of rigid JVM, then you have to do this. And yes.
And the good thing is that you will impress your manager.
But what if, just an idea, what if you can keep this command line, but in the background there's a JVM who you don't really have to worry what's on there. What if that's possible?
Is it helpful to look at the problem a little different when it comes to memory as well sometimes? I mean, a lot of times...
I can't hear you, sorry.
Does it help to look at the problem a little differently sometimes? Because a lot of times we have objects in memory that they're not really garbage. They're being marked and swept. I mean, caching is a perfect example of this. And you've got Terracotta with big memory who's got the off-the-heap memory allocations they have. Why isn't something like that moved into the JVM as well, so it's a feature of the JVM to have essentially off-heap manage objects when the application knows the life cycle of the object, when it should be evicted and thrown away essentially?
That's a very good question. I think that's why caching technology has spun off to be so beneficial and popular these days. Caching is really something we see implemented everywhere. It's to solve this scale-out problem.
Right.
And again, I'm restricted not to promote my own product, but there are JVMs out there who has solved the scalability issue that allows you to host hundreds of gigs in memory without cost times.
So they're doing off-heap memory management.
We don't do off-heap, we do on-heap, but we've done compaction in a concurrent way. We don't need off.
So another way to put it is just the defrag example. So Windows on the file system, you got to defrag your system every once in a while.
Mm-hmm.
Most Linux file systems, you don't need to. It always keeps doing it in the background. That'd be a similar analogy, what you just said.
If I will try to use that on Windows, when you have to stop what you're doing to defragment, because you choose to do that then, and then compared to Linux, you do it in the background. That's basically a good analogy, I think, but
not exactly the same.
Not exactly the same. It's exaggerated, yes. But what we do is basically decouple the virtual address space from the physical one, and it's patented, so I feel very safe talking about it. And we use a read barrier to check if a reference pointing into the virtual address space has moved, and then that application thread does that update. And you don't really have any stopped and temporary one just for that thread.
It's similar to that virtualization idea. Yeah, it's okay.
But we don't do off heap because there's a cost of doing that, right?
But there's also a consistent performance line as well too. If you're dealing with pauses, you know, your performance is going to be variable. You're going to have hills and valleys. But if you're dealing with off-peak, performance levels out because you're no longer market sweeping a large heap at that point. It'd be, you know, 1 gig heap or 512 gig heap, but you've got.
Depends on how costly it is to access that off-heap area.
You're not going to get as performant as on heap for sure.
Right.
But it's consistent, so you can deliver 5 nines SLA because you've got consistent execution. You're not having to worry about these spikes in GC at any point in time.
But I like Java and in-memory. Okay, I'm going to round it off. So I talked about the biggest Java limitation is the stop-the-world compaction. And I look forward to more innovation in this area. I work with a very interesting company who has one innovation in it that actually does concurrent garbage collection, but I'm not here to talk about that. And 2 cents for the road. Here are my personal 2 cents from all the years of JVMs and JVM running customers who run into weird things. Most Java applications I've seen is single-threaded, although most believe they are multi-threaded. Over and over it proves itself. They think they are multi-threaded, but they are not. Make sure to verify that.
I'm sorry, could you elaborate on that?
So people think they are using multiple threads, but in the end, when you see on the thread level, like from the JVM end, you see that it's only one application thread allocating objects. It's not 10 concurrent ones or 200 concurrent ones as the customers usually claim. It's some thinking. I think it's very interesting psychological phenomenon that I've seen. I think we are single-threaded in our brains, and that's how we implement Java. It's hard to think several threads and how they interact, but you know, you are experts in this room, so I don't blame you. This is an observation what I've seen out there.
This is true for web applications where you just keep on handing out. Right? So,
I don't know. I've seen it.
are
Stay
there
away from
applications
weak and
or
soft
stuff?
references, please. Finalizers, all that. Please, if you can avoid it, don't.
If you're using a finalizer, though, for cache management,
Yeah, it's very popular to do that.
how else do you do it? How else, because there's no destructors, how else do you know that there's
Okay.
nobody left holding it?
Do it, but carefully don't.
Don't
I
get
mean,
carried away.
the GC, the JVM has to keep everything if you do anything that reference everything from that finalizer. Be very careful if you do it. I don't recommend it, but you know, if you have to, you have to. It's there.
It's sort of like making sure you put a finally block in your JVC statement thing or whatever to make sure you clean up the features. So you better know what it is that you're doing.
You better know what you're doing.
Speaking of
We have seen so many bugs and so many horrible memory leaks and difficult worst case use cases
Maybe.
using finalizers the wrong way. But again, I'm trying to wrap up. Always be careful around locking. Whatever you measure in your lab, looks fine. When you get out into production, you know, it would be good to do a little profiling there too to see what locks actually get really hot. And there are many good profiling tools to do that. But those are very common Java performance bottlenecks, is hot locks. Blocking threads of doing their job, right? And my personal, you know, dislike of benchmarks. But yeah, they're good to show, you know, published results of how much throughput you have. It doesn't really show how responsive your web app will be once you have 2,000 concurrent users waiting for the page to load. And here's the summary. Yes, there's a quiz from my dear coworker Kathy. And
No, I'm not giving a quiz.
Patient Doug there in the corner, waiting all evening for me to stop talking. Here's some references, some more to read, or a webinar about process GC that we have on our webpage. If you want to see it, just go to Azul Systems. So, what have we learned tonight? So raise your hand if you want to answer, so I can see who's first. What's the biggest Java limitation, scalability limitation out there?
Compaction. JVM compaction.
Stop the
Heap compaction.
world
Yeah, stop.
compaction.
All those things. Thank you.
Okay. How many commercial compilers are there in a commercial JVM? Like, what are the compilers?
Client server too?
Client server?
Tiered,
Yes.
3, according to what your slide
Sorry.
said.
There were 3?
3.
Client
I
server
mentioned one
tiered.
briefly. The tiered, that is unique to one specific JVM. It uses profiling data, code profiling data from client, which is, less intrusive to collect, but uses that in an intelligent way to execute optimizations from the server side compiler. So it's faster and better. 6 times the performance versus interpreting compiler. 2 more. Kathy, do you have a favorite question you want to ask?
Stay on here, that's about it.
Actually have, so what kind of garbage collection algorithm is used for nursery?
Generational.
Raise your hand.
Okay.
Mark and Sweet.
No.
Copy.
Yeah. And last one,
What was the answer?
copying garbage collection is used to collect the nursery. And what else? What is the only optimization example I presented today?
See, we're not raising hands anymore.
All right, thank you.
Warning to add behavior.
Yeah, questions? I think we covered a lot. Yes?
It seems like there's all these trick algorithms for moving these objects around in these different spaces and when to move them and stuff. Do any of the VMs have features that the application can say, look, these objects are going to stick around a long time. Don't even bother with the young generation, the medium generation, the old. Just stick them high up there. I know I'm going to keep them until the thing dies. Is there
Yes.
any? They have those that.
Yes. There was a thing called pinned objects, or there's also perm space. I think.
There's also real time Java.
Guess what developers do? Throw their objects up there.
There are many talking people at the same time. Yes, there is different approaches to that. One is pinned objects. So through the mark phase, you kind of know by a bit set in some bit vector that this object should not be. That's one approach. Another approach
What
is
should not be moved out of the young generation?
not be moved at all. Stuck.
Sticky.
Usually they are allocated in the whole old heap directly, if they are a pinned object.
And where does that, as the application builder, what is that, some extra file that's read by the VM startup or something? Or?
It's usually a certain type of application, like a class class object may not be, you know.
So the behavior of the VM internally sticks certain objects in certain places. But I was thinking of some application object, like my cache manager or something. Is there ways to teach the VM, look, I'm going to start one of these and it's going to be there. So can you put it in the right place first, instead of moving it around, and its hash tables, and its lists, and its,
I'm thinking there must be a way, but nothing comes to mind right now.
You do it off heat, but that's.
Wouldn't
That's
assigning.
I think that was your comment here.
Yeah.
But you could, NIO package, you can store it off heat, but that's.
Yeah.
Wouldn't assigning
Well,
the object.
I'm not in the off-heat land, yes.
It's way too much to sort of
I asked a little earlier about the question about this 4 gig limit, which I've heard before. Is what is that actually a hard limit at 4? And if so, where does 4 come from? What is this issue about
So
4
it
gigs?
is about per 2 gigabyte, there's a cost response time increase of, and I'm failing to remember the exact number here, but I think it's like 1 second per 2 gigabyte heap size or something like that, a few seconds per 2 gigabyte heap size.
Is it linear though, or is it exponential with the heat? Because if it's linear,
Let's
then-
just assume it's linear, but it actually depends on how complex the data is, how many references, and the sizes of objects and the live rate of objects, because if many small objects next to large objects die, you know, it will affect the situation. But let's just assume it's linear and that the data is random sized and random complex and random life rate, and it's allocated at, you know, some average allocation rate, if there is such, then, you know, usually what we've seen proven in practice too, by 4 gig, you won't hit those 5-second pause times that break your SLAs. And 5 second is a very common SLA response time requirement for most web applications that I've seen at least. And you can object and say other things, like certain low latency transaction apps may have different SLAs, but they usually have the smaller heap. So 4 gigs is kind of the pain level that we've seen, and it depends on that. It's, you know, 1 to 5 second pause time dependent on your app. We have seen 16 gig applications, but they are less sensitive to the response time then to be able to run that. They have 10 seconds of response time, but they're, you know, it may not be mission critical.
How often is it doing that 5-second pause?
As often as you garbage collect.
Right, well, that's the obvious answer, but.
It's hard to answer those questions
I mean,
since it's application dependent, right?
Right, I mean, this is a small garbage collection going on all the time, right? And there's the big garbage
Mhm.
collection that goes on, that's the 5-second pause. Or are you saying even the small pieces are
I'm
expensive?
talking about the worst
Yeah.
case pause time, which may not happen for a while, depending on the application, how the objects look like, and how much fragments are created that cause that full stop the heap compaction. And that is, I'm talking about the worst case pause time. I'm not talking about
So a
the
trading
average.
program, you don't want a 5-second pause, you know, somebody's
Right.
trying to make a trade, right? But if you're buying something at Amazon, you know, it doesn't
That's
really
the
matter.
worst case pause time, I guess. It's not the average.
Hey, how many other players are there in this space? We know Oracle, we know Azul, is IBM, how many,
Yes.
you know, who are the other players in this
So
market?
we have OpenJDK, right?
Yeah, okay.
We have Sun Hotspot, Oracle Sun JVM. We had JRockit, it's still around, but it's also Oracle, and I think, I don't know what the latest is on the roadmap for those. We have IBM, JVM, J9, and we have Zing. And it's the same technology in Vega, her older product line. So I would say 3 vendors, commercial vendors, from which one has, two commercial and one open source.
Does Apple have?
But then JRockit comes in different versions too. So it depends on how you count.
But
I'm just saying that Apple.
Oh, I didn't count the mobile ones.
Yeah, I was gonna say Android. I mean, that's
Yeah, okay. I stick to server side.
I was talking about, server side, big memory solutions.
Yeah, there are some mobile vendors who have
Yeah.
JVM.
Yeah, I wasn't asking about JVMs, I was asking about this space, which is high-end, mini gigabyte, mini processor thing.
So I would say 3
Okay.
commercial vendors that I'm aware of.
And Apple's is just Sun's hotspot.
Well, Red Hat has also their JVM license from Sun as well.
But
But
you're
I count
basically-
the source as.
Eva, question. What about solving this problem kind of at the system level? So what about a stateless architecture, multiple VMs? So you don't have to worry about one of them processing.
So you mean like clustering JVMs?
Yeah.
Yeah, that's
Some
fine.
mistakes.
If you want to handle hundreds or thousands of JVMs when you're in a production server side load.
No, I'm just talking like 2 or 3 or 4. I mean, you have to have
Yeah,
HA
before,
redundancy.
I mean, if that's all you need, then.
How would your load balancer know that this particular VM has gone off to garbage collect?
You just listen to the first one that you present a request to every JVM, and if one happens to do a big collection, you'll get the response from the other one first.
But
redundancy, you can ask a couple.
Yeah.
But I've seldom seen a production environment with 2,000. Yeah, and not only that, your environment becomes more complex to manage and upgrade and monitor and all
Yeah,
that.
but some of that's already there. Most places that have been going to digital high availability have at least one stack along with your section stacks, a standby, whether it's a hot standby, a full standby, whatever it is.
Obviously, you love to interact with people with the large servers. What are the folks in the JVM at the technical conferences talking about when they put the VM on the phone? What assumptions can they make, and are they all simplifying? We'll assume they're mostly simplifying assumptions, but what are they assuming?
A JVM on a phone is very different because it has to be, energy efficient and living in a smaller space. So I think it's very, very different challenges there. You have to think about battery time and.
So you can't just run around looking for things to throw away all the time and use up your phone by sunrise.
Yeah.
When you listed commercial implementations, you did not mention real-time implementations. Was it intentional? So what?
So real-time, you mean real-time Java implementation? Yeah, then you have to recode and you have to follow certain restrictions. It's not the full Java language flexibility, but that, it works as advertised, I guess.
You mean,
I have avoided that intentionally because I'm not an expert on it.
What kind of restriction do you know? If it's say can run any standard Java code, does mean restricted. What kind of restriction?
I'm not that detailed into real-time
You
Java.
can't stop the system.
But I'm sure you can find information on the Java website. I don't know how to answer. I'm sorry.
One of the things that really seems to slow down compaction is the fact that the operating system probably just decided it's going to swap out half of your